So very good evening to everyone. So myself Mohammad Asheef, and I am thankful to all for giving me this wonderful opportunity to be a presenter of this topic. Today we are going to involve the topic of protection relay scheme based on fault reactance operation type. So the main motive of the study is to improve the computation time of relay and to simpler explanation of the principle of the relays. So what is actually a protection relay? So when we go inside the protection relay, the main type the protection relay works on, the current differential type based on Kirchhoff's first law and the impedance type based on Kirchhoff's second law. Due to this Kirchhoff's law that rigorously formulate the fault phenomena. So the circuit equation are presented on a non-linear simultaneous equations. So those that the fault location and the fault resistance can be accurately pointed out. There are two defects that are involved when we are using this concept of Kirchhoff law. One is there is a heavy computation burden in iteration calculation of Newton-Raphson method. And the other one is the relay operator cannot easily understand the concept. There is much more computation and it not being easily understand the principle of the least numerical matrix operations. So the summary of this paper. This paper is completely focused on the fact that the reactant components of the fault point is completely zero. This this paper is principle proposed in this focus thing. The reactance of the sending fault reactance and the receiving fault reactance at the end of the branch is collected, calculated by the solution of linear equation. If the sign of the sending fault reactance and receiving fault reactance are not same, it can be interpreted that the fault point is located in a branch. This reactance is corresponding to the difference in with the branch reactance. When the actual fault point and the imaginary fault point of the specific fault reactance is not being seen. Thus, the relay engineers can understand the fault location in the concept of distance. So, if we go with the distance relay, actually we see only the reactance in the system. On basis of the fault occurs in the system, we see how much reactance we compare min and So, so by this concept, this gives the more precise estimates location of the faulted system or faulted branch, which is faulted by either like natural fault or is by animal fault or the fault occurs in the system. It can precisely estimate the fault location. So, being the introduction of this relay, the first before the years we are using of mechanical relays. Now it dramatically changed, and the improvement of the relay concept is dramatically changed. Like if we say before that year we are using mechanical protection relays. Now we move forward into the digital relays. This is a numerical digital relays. This composed with CPUs. This composed with the CPUs and the programmed one. So this gives the system more protection reliability. So if you have the system with a numerical relay, it is more efficient than the mechanical protection relays. So in other hand, this principle is possibly most rapid growth in CPU. So if we see in Japan, the current differential relays requires the information on other side of that relay. Once a false occurs in a system, they require the information on the other side, mainly for protect power transmission lines above 154 kV. While in the line section relays and distant relays are employed with the line below 77 kV. In the later cases, if you say the fault of location accuracy is 10 to 15% only, it depends on they are moving with the matrix concept. Since the fault that occurs near on the other side terminal buses causes serious tripping on the break steps. They have the fault location the precision of the fault location is not reliable. There are the larger number of double circuit common terminals. If a double circuit fault occurs in a system, there is a more probability the backup protection will also get triggered. There is an increasing number of double circuit faults. Combination. So the impedance and reactance used in the later relay schemes are designed to identify the fault points, whether the voltage drop to zero. So once a fault occurs in the systems where the resistance or the reactance in the system thus go to zero, then the voltage drops to zero. On the other hand, it is not the fault, it is not the thing is going to happen. But the point is close to zero, but it is not to be zero, it is close to zero. Then the fault occurs in a system like 3, 4, 6 indicates the assumption of xy equals 0 offers high location accuracy. But when the reactance occurs, when the fault location of the faulted location is not a 0, then the term of accuracies get reduced. In the matrix type protection, the relay proposed previously in the reference file, the transmission line faults are formatted in terms of Kirchhoff first and second law. The numerical relay they uses the two concepts. As I said before, it is current differential type and impedance type. So the current differential type is work on the scheme or on the type of Kirchhoff first law, and the impedance type is work on the principle of the Kirchhoff second law. So the relative fault position, the K denotes the same thing where the fault is located, where the fault is pointed out. X of the reactance, the fault reactance equals 0, and the fault resistance are found in the matrix operation. In the field test, so they have gone toward the field test on 66 kV double circuit transmission line. The location error was 0.2 kilometers, but the line length is completely 14 kilometers. They have conducted 18 cases. From that, the correct operation they are precised to be 7 cases only, and the non-corrected operation in 1 case is attained. The problem with this method is the long time consumed by the iterative calculation to solve the nonlinear simultaneous equation. When applying to the multi-terminal transmission lines, the method must be modified. So as to deal with the linear equation, the logic must be improved so that the operator can easily understand the relay operation. The most important operating task of the protection relay is to identify the fault and improve the reliability of this system. So incidentally, the matrix type relay find the location value. So find the K value and they taken the K value as a variable. Since the fault reactant SF is basically 0, one can find the XF assuming the fault occurs on the section boundaries, like both we can say as bus and branch point. Then, when XF equal to 0, can be checked interpolation of internal fault. Fortunately, the XF correspondingly close to the line of reactance and assume that the fault node from the true fault location. Therefore, the opposite side indicates the fault reactant is a system that ends in an internal fault. Then the same sign, like a positive sign, indicates an external fault. These are the things we can easily manipulate from that. When the fault reactant in the system got to negative, the sign of opposite thing, then we can assume that it is an internal fault. When the fault reactant in the system is the same sign as the positive, we can determine as external fault. In conventional one-side measurement type protection relay, the distant fault where they are considered that the voltage drop to zero is measured from the PT and CT installation points. The proposed scheme differs from the fact that fault location is determined with respect to the protected system. Since as I said before, in matrix type, they treat the K value as a variable. and XF is a linear. By the mean, we can get the XF as a linear equation, which is very important to practical implementation. It takes the computing time is more. So in this paper, so we are working to propose a fault reactant operation type relay and the result verification of location frequency performance in a field test. So once we taken a transmission line fault simulating the two circuit, then we have the two circuit like the first circuit as we see here. That we see here, there are the two circuits. So the circuit 1 and the circuit 2. There is a two transmission lines. Like in the one transmission line we have three terminals, 1, 2, 3. Like we can say is our YB or ABC, whatever we think. And the second transmission line has the same three terminal 2, 5, 6. So these are the two line circuit in a transmission. So the first of all, which indicate VF1, VF2, VF3. This is all the fault voltages. So when the fault occurs in a system, they the occurrence of voltage it indicates the occurrence of voltage. In the second circuit, we see there is a VF4, VF5, VF6. We named as the completely as six terminals in a system. So when the first of the terminal they have the denotation of IF1, RF1, XF1, where IF always donate the fault current and RF which donates fault resistance, and XF we actually know it is a fault reactance. So when the fault occurs in a system, these are the components present in the systems. So the fault current flows into the ground through the fault impedance or plus X. So when the fault occurs, we can completely say it is an impedant one when the resistance and reactance both occurs in systems. So what is V? What is the tower potential? The this tower potentials only occurs when there is no contact in ground. When there is a fault is no contact in the ground. Like we can say line to line flow. So when the line to line short fault occurs in a system, then there is no VT is occurring because the contact with the ground does not take place. In a single line to ground fault, we can say in the number one the parameters IF, RF, and R equal. Then the VT is also given because once a ground is present in the system, then the potential the tower potential is considered to be zero. The proposed concept of the fault characteristics deal with one fault in the section, and we have simulated completely with the multiple location. Then the multiple locations are we have we have come under the scenario of 8 cases, like 8 fault cases. So let me see one by one. So one for a simple understanding and a physical meaning of what is a fault reactance, how it is occurred. So we have taken a transmission line, a single line. There is a as we see before, we have this transmission line with the three terminals. So in that we have taken a one terminal line for our better explanation and understanding. So this is a source voltage and K we always know it is a fault location and this is CT and this is a VT. The potential transformer, this is a current transformer, this is a fault located in the system where we are getting the sending end, we are receiving end voltage and there is a load is connected at the end. So if we see this K donate the fault point or the fault located in the system. So this is an equation we can get from this above transmission line, where VPT donates that it is a potential transformer voltage. The voltage of the potential transformer is equal to K is the location of fault equal to the impedance occurs in a system Z into ICT, the current transformer, the CT in the current transformer, plus RFIO, the fault resistance and the current and the fault current. So the V is equal to K, the impedance plus the current, CT current, impedance that CT current plus R of IF. So this is the equation we get from this above transmission line. So this ICT is equal to IF and IL. The whole current that passes through a CT is equal to IL plus IF. When we here to find the IF, so IF equal to this IL is coming in this end. We can say ICT minus IL in the second equation. So we are taking the IF and multiplying in the both end of this first equation. So IF equal to VPT equal to K IF into Z of ICT plus R of IF into IF. Now assuming the identical value of PT and CT in the figure 2 we can see in the next slide, considering the fault reactant X as a circuit rotation. So the first transmission line we are changing this K into X, and we are writing the same equation the second with the VPT equal to X Z of ICT equal to Z of X and Y. So for this K terminal, we are indicating this R of resistance R of into impedance law. Completely impedance. We are changing into this resistance into an impedance thing. So finally we got from the above these two equations 1 and 4, where Z equal to K minus Z ICT plus IF plus RF. So what is the relationship between the thing actually? So when we came across the thing that where the X donates there is a location and K donates there is another location in the transmission line of fault, and the X of is a fault reactance. When X equal to 0, when this the fault in X is equal to 0, please donate the X of reactance is also 0. If you are taken, it is a 0, 10, 15, 20 kilometers. But the K point actually we can take as a simple thing we can assume that the K is 20 kilometers, while the X is it's greater than 20. So if K is 20 kilometers, so when the fault occurs in a 20 kilometers locations, so we can say the X of is equal to 0, the same point. As that it increases when before the fault, before or after the fault, we can say this the X is going to the same point where it comes under a stable position. So before a fault, the X has some has some resistance in the system, reactance in the system. When the fault occurs, is come to 0. This the relationship between X and XF in the equation. We can say XF equal to K minus X. At last we can get this one. Therefore, the XF has a different sign on the branch nodes. Then XF equal to 0 on the fault location is present. So at last we can precise that at fault location 0, the fault location, when the fault occurs in a precise location, we can say that the XF will become 0. And the K can be found on the different center. So we have taken a field test, this test of transmission line, thus contain a double circuit, and there is a generator that feeding toward the load, and we have at n equal to SWS we have kept the relay at the end. This is a starting point IPS. The transmission it is a 66 kV double circuit transmission line at the length of 14.3 kilometers. This is connected to the two power station PNS connector. The single circuit transmission line runs from this generator source 46.9 MV, and the relay, as I said before, the relay is installed at NSWS. So using the CT and PT that stores the values before the fault and after the fault condition. So we have already said that we have a scenario of 8 fault that occurs in this transmission lines from the period of 1 year. It started from October 2003 to September 2004. The information that we summarize, that the fault calculation results and the location of the fault that occurs in a terminal. These fault lines are identified by inspection toward the field and by using the oscillograms. Now the K actually say the K denotes that relative position of the fault station, and the KD is the distance. This denotes the distance in kilometers and K denotes at a perimeter. So first we can say we have 8 types of fault occurs in a system, and we have 6 terminals. When we have 6 terminals, we are using double circuit. We are using double circuit. For one circuit we have 3 terminals, and other circuit we have 3 terminals, like 1, 2, 3, and 4, 5, 6. So when the first fault occurs, so the fault per unit, we actually per unit is taken as 1 for a complete one. So the location is 20.4, but our system has only 14.6 kilometers. The fault occurs in a system of fault lines circuit 1. The second terminal got faulted. It is by monkey electrode. So we get the per unit. This is a fault expert and this is an inspection results. So the fault per unit and the system we can calculate and beyond that. It is outside the thing. How we analyze and receive this outside it is. Our complete system is 14.6 kilometers only, but the fault occurs at 20.4 kilometers. So it is outside from our point. The second fault is by unknown patrol, and a third one is by galloping and a bat and birds and a lightning. These are the things. And we got the every 7 faults that occurs inside the system and 1 fault that occurs outside the system on the period of 1 year. So from the conclusion, so we have the from the old one it is matrix operation, and we have proposed the fault reactant calculations. So in the matrix operation, the fault location inside the section is treated as the fault location. As I said before, the K is a fault location. In a matrix type, it is treated as a variable, and the circuit equations become non-linear. The greatest problem in iterating calculation required in order to solve such a non-linear equation, it takes a computing time is a large. So in a matrix type relay, the proposed previously by the author, the K is calculated by using predefined matrix. On the other hand, this is a present study, only 3 matrices are used in the linear calculation. So for taking the system K in a variable, from this complete thing we can understand in a matrix operation by taking the fault location K as a variable, and taking it as a variable, it makes the system into a non-linear thing, and it increases the computation time. And the error occurs in a system is 10 to 15%. But in a proposed fault reactant calculation, the fault are assumed at the both end. So we have taken and we have assumed that it occurs on both end of the line. So if the fault reactance found opposite sign, we can say it is an internal fault, and on the fault reactance is in the present sign, we can say it is a we can say it uh, is a physical distance. Based on the new approach, we developed in a program of fault characters and verified in accuracy the actual fault required in the field. We found that the fault lines and sections are identified properly, and the location error is reduced to 5.5% on the average. This significant which improves the conventional differential regress. So the basic underlining the fault reactant approach in the system that we can accept the following new function due to the employment of proposed protecting relay schemes. So these are the things that we occur that the integrated protection against a ground fault and a short circuit fault and an integrated main fault. So these are the things that integrated protection against ground fault and a short circuit fault, the integration of main backup protection and a relay output. So these are the things we get improved. So thank you for giving me this wonderful opportunity, and once again thank you for the thing. Thank you.